On October 29, 2025, the sky will hold its breath. Somewhere behind the Sun, completely obscured from every telescope on Earth, an interstellar visitor named 3I Atlas will reach its closest point to our star. For 3 critical weeks it will vanish into a corridor of light so blinding that even our most powerful observatories will be rendered useless. And that is precisely what has scientists awake at night. The timing could not be worse. So before we continue, leave a like and subscribe, only if it truly feels natural. And now, softly, tell me, where are you listening from? No human in recorded history has witnessed this exact circumstance, a confirmed interstellar object disappearing exactly at the moment of perihelion, the moment when sunlight would have stripped away its secrets and told us what it truly is. Instead, 3I Atlas will be gone like a messenger stepping behind a curtain just before it speaks. The news broke quietly in late September. There were no headlines, no government statements, only murmurs through the astronomy community shared through private mailing lists and encrypted conference chats. "It's going behind the Sun," someone wrote, completely behind it. A pause, then another reply, "You're kidding." That's when it reaches perihelion. The realization spread like an echo for 3 weeks, the most chemically unusual object ever detected. An object showing emissions no natural comet has ever displayed would be invisible. NASA confirmed the alignment. The European Southern Observatory confirmed it again. And by mid-October, every observatory on Earth was preparing for the most frustrating silence in modern astronomy. From the deserts of Chile to the mountaintops of Hawaii, telescopes turned their domes toward the blinding solar glare and calculated how close they could aim before sensors would saturate. They could do nothing but wait. For astronomers, waiting is a strange kind of pain. Every second counts when an object is this rare. Interstellar visitors, rocks, ice, or something else entirely cross the solar system at enormous speeds never to return. They are cosmic refugees born around other suns and thrown into the void by violent gravitational accidents. To miss even a few hours of observation is to lose information forever. To lose 3 weeks is to surrender answers that may never come again. Yet this is not merely a technical inconvenience. There's something almost poetic about the timing, something that touches the same nervous place in the human imagination that ancient eclipses once did. Thousands of years ago, our ancestors watched the sun vanish behind the moon and believed the world might end. Kings fell to their knees, empires paused their wars, priests whispered that gods had turned their faces away. Today we do not fear the sun's shadow, but the feeling is faintly similar. When a scientific mystery slips out of sight, the rational mind trembles with the same awe that once drove people to build temples aligned with solstices. It's the sense of standing at the edge of knowledge and realizing that the light we depend on for truth can also blind us from it. The astronomers call it solar conjunction. The public, if they notice at all, will call it nothing. But in observatories from Japan to California, there will be quiet rooms filled with caffeine data models and a strange kind of anticipation, because on the far side of the sun, an interstellar object will undergo its greatest transformation when no one can see. By the time 3 Atlas re-emerges in November, its appearance could be utterly changed. It might fragment, it might brighten or dim. Its path might deviate slightly, an imperceptible curve that says everything about whether it is natural or engineered. We will not know until it returns to view. That ignorance feels almost personal. Science at its heart is a conversation between light and attention. We ask the universe answers slowly, faintly across millions of miles. And now the voice we most want to hear has stepped behind a source of silence so absolute that even the James Webb Space Telescope must wait for the geometry to shift. Avi Loeb, the Harvard astrophysicist who stirred controversy by suggesting that Oumuamua might have been an artifact, phrased it simply: "If you wanted to make a maneuver unseen, this is when you do it." He meant it as a technical observation. Perihelion offers maximum leverage for propulsion, but the phrasing caught on. Forums lit up. YouTube thumbnails screamed the perfect blind spot. Journalists asked NASA for comment, and NASA predictably gave none. But for the men and women tracking the object's fading light from observatories around the world, this wasn't about conspiracy. It was about the exquisite agony of data gaps. Each night they checked the ephemerids, recalculated trajectories, adjusted for solar wind perturbations, and then stared into the glare where the object should have been, somewhere beyond the corona wrapped in plasma, its surface vaporizing under the sun's relentless heat. Imagine that moment, the universe staging a drama just out of view. Behind the star that sustains all life on Earth, something from beyond our solar system is passing unseen, unknown. It's not fear that scientists feel, it's humility. The same humility ancient astronomers felt when they watched constellations slip below the horizon and realized that knowledge always has an edge. For 3 weeks, the world's instruments will blink into blindness. Spacecraft near Mercury radio, arrays on Earth, even solar monitors will see only glare. And then sometime in mid-November, Atlas will emerge once more, cooler, altered, perhaps whispering through spectra what it endured behind the sun. Until then, we wait. The countdowns have begun. Observatories have scheduled their observation slots. Data analysts are rehearsing the moment when the object reappears, and somewhere in that collective anticipation lies a truth older than science itself. That wonder often begins not with what we see, but with what we cannot. The sun blazes on indifferent, and behind it, hidden from every eye on Earth, moves a visitor that shouldn't exist. The language of orbits. Perihelion, the word sounds clinical, distant, born of equations. But in truth, it is one of the most intimate moments in the life of anything that travels around the sun. It means the point of closest approach when an object surrenders to gravity's embrace and passes through the heart of its orbit. For comets, it is a moment of revelation. The sunlight that once caressed their frozen faces from afar now burns them bare, vaporizing ice into gas, releasing ancient dust that has not seen starlight since the birth of its parent star. Astronomers describe perihelion with numbers, distances in astronomical units, angles of inclination, eccentricities that define how stretched the orbit is. But beneath those abstractions lies something deeply human, a pattern of closeness and retreat, like the breath of a dancer who circles a flame. Everything that orbits planets, comets, spacecraft, even light itself, participates in this cosmic choreography. Picture the solar system not as a static model of circles on paper, but as a living dance floor illuminated by a single fire. Each world moves to a rhythm carved by gravity, every orbit a measure of that same universal song. Mercury twirls tightly, its year only 88 days long. Neptune drifts at the edge, its slow waltz taking a century and a half. Earth keeps steady time, always returning to the same point around the sun, every 365 days, a heartbeat of habit. And then sometimes something arrives from outside the music entirely, something with a step unfamiliar to our rhythm. That's what 3i Atlas is. It does not belong to this dance floor. It came from beyond the sun's kingdom, a traveller flung from another star's gravitational hand, crossing the black gulf between systems. Its orbit isn't bound like ours, it's open, hyperbolic, a curve that never closes. Once it leaves, it will never return. But in the few months it spends passing through our celestial stage, it follows a choreography, dictated by physics so precise that it humbles even the most skeptical observer. Orbital mechanics is not chance. It is inevitability expressed in motion, a kind of cosmic grammar. Every body, no matter how rebellious, must bend to the syntax of gravity. And yet the story of 3i Atlas seems to whisper something else, a subtext beneath the mathematics. Because when scientists plotted its trajectory, they saw not chaos but alignment. The plane of its orbit runs almost perfectly along the same thin disk that holds our planets. The timing of its perihelion coincides almost impossibly with Earth's position directly opposite the sun, rendering it invisible exactly when we would have been watching most closely. Coincidence, says the cautious scientist. Probability can produce even the rarest symmetries given enough rolls of the cosmic dice. Intention, murmurs the dreamer, or at least the question of intention. To understand why this moment matters, imagine the sun as a campfire surrounded by wanderers. Each planet keeps its respectful distance, finding warmth without being consumed. But every so often a stranger approaches from the forest's edge. The firelight catches its face for an instant before it moves on into the dark. That instant, that fleeting nearness, is perihelion. It is the moment the sun tests the stranger's truth. Does it burn, break apart, reveal its inner elements, or does it pass through unchanged, serene and silent, like something built to endure light itself? For most comets, perihelion is catastrophic. Their icy skins erupt, tails bloom and pieces scatter into orbit. But if 3i Atlas emerges from its passage intact, it will defy that expectation. It will tell us wordlessly that its nature is not as fragile as others of its kind. And that would mean our first glimpse of an object born in another system, perhaps even another age, is something far tougher than we imagined. Orbital mechanics, for all its precision, has room for wonder. It tells us that motion and meaning are sometimes the same thing, gravity translating mystery into rhythm. Every ellipse, every spiral, every arc is a story written not in ink but in inevitability. The ancient astronomers knew this long before Newton gave it mathematics. They watched the sky and saw gods in motion, Mars as a warrior, Venus as a lover, comets as omens. They were wrong about the details, but right about the poetry. The heavens do speak, just not in words. So when scientists today speak of perihelion and trajectories, they are in a way translating the oldest language in existence, the language of orbits. Each curve in that language has meaning. Each deviation hints at intent or accident. And when an interstellar traveller happens to follow a path so exact, so improbably aligned with our own planetary plane, the line between coincidence and design begins to blur. It is possible, of course, that 3i Atlas is nothing more than a rock, a relic flung from some long-dead world around a distant sun. But it is also possible, however faintly, that this is something more deliberate, a fragment of purpose hidden inside the cold laws of celestial motion. For now, all we can do is watch its path curve toward the sun and wonder which it is randomness written in light or choreography whispered by something unseen. The language of orbits doesn't answer. It only repeats its eternal refrain. Everything that moves is drawn toward something, the chemistry that shouldn't exist. When light passes through a comet's coma, it carries secrets. Each wavelength, each subtle flicker of colour is a confession written in code. Astronomers use spectroscopes to translate those confessions, splitting the light into rainbows so fine that individual chemical fingerprints appear like bars on a cosmic barcode. In those patterns, we can tell what an object is made of, even from millions of miles away. In early August of 2025, the Very Large Telescope in Chile did just that. It turned its mirror toward 3i Atlas and found something that made experienced chemists sit up in disbelief. There, hidden in the emission lines, was the unmistakable spectral signature of nickel tetracarbonyl NiCO4, a compound that no natural process has ever produced. Nickel tetracarbonyl is not a mineral. It is not found in comets, planets, or stars. It is an industrial gas, a man-made substance created only in laboratories or factories on Earth, first synthesized in the late 19th century. In human history, it has been used primarily for refining metals, a way to extract pure nickel through a process of chemical vaporization. The method is ingenious, dangerous, and deliberate. To make it, you must expose finely divided nickel metal to carbon monoxide under precise temperature and pressure conditions, neither too hot nor too cold, neither too oxygen-rich nor too starved. If you succeed, the nickel atoms join with carbon and oxygen in an exact molecular geometry, forming a colorless volatile liquid that evaporates at room temperature. It is highly toxic. A single breath can be fatal. It decomposes into pure nickel and carbon monoxide when heated, which is why it was once used to plate metals in factories. The point is, this compound does not just happen. It requires both energy and control, the kind of environmental fine-tuning that nature rarely if ever performs spontaneously. The interstellar medium, by contrast, is chaos radiation, cosmic rays, random collisions among frozen grains of dust. The conditions are brutal but not orderly. And yet 3i Atlas was producing nickel tetracarbonyl about 4 grams per second of it. When the data was first reported to the spectroscopy team, they double-checked for instrumental error. Maybe the emission lines were misidentified. Maybe the calibration lamp was faulty. But when the European Southern Observatory repeated the observation with a separate instrument, the same signature appeared, 4 carbonyl bands, clear as day at wavelengths no one could mistake. To make matters stranger, there was no iron in the mix. In every comet ever observed, nickel and iron appear together, the twin metals born from the same supernovae that seeded the universe with heavy elements. To see one without the other was like finding a fingerprint without a hand. That single discovery, nickel tetracarbonyl without iron, cracked open the entire conversation about what 3i Atlas might be. Because if those emission lines were real, then either our understanding of cometary chemistry was incomplete in a way that strained credulity, or something about this object did not obey the natural recipes we know. And here is where the story becomes uncomfortable. Humans tend to recognize only what we already understand. When we see a spectrum, we match it against our library of known molecules, nearly all of which are earthly. The spectrographs are, in a sense, mirrors of our own civilization's chemistry. So when astronomers say it looks like nickel tetracarbonyl, what they really mean is that its light behaves like something we've built before. That could be coincidence. Spectral coincidences happen. Different molecules can mimic one another's emission lines. But it could also be a sign of our own bias, the anthropocentric filter through which we interpret everything we see. The universe might be telling us a story written in its own chemical alphabet, and we keep translating it into ours. Still, the discomfort lingered. Nickel tetracarbonyl is rare not only because it's artificial, but because it's fragile. It breaks apart easily under ultraviolet light. It cannot survive prolonged radiation. And yet here it was in a coma, bombarded by solar photons and cosmic rays, persisting long enough to be detected from Earth. To some, the explanation was simple. Perhaps a natural nickel compound on the surface of 3I Atlas was decomposing under solar heating, releasing transient nickel carbonyl vapor that quickly vanished, a fleeting chemical coincidence, not an industrial mystery. To others, the coincidence was too precise. If one were to imagine a machine designed to process metal in vacuum, to harvest melt, or refine using solar energy, one might expect to find traces of exactly such a compound. But scientists are cautious with imagination. Avi Loeb phrased it carefully in a late-night interview. We're not saying it's artificial. We're saying the chemistry doesn't fit. And when nature doesn't fit, you look closer. Behind those words lies the quiet humility of science and its vulnerability. We build our models from what we've seen, but when the universe shows us something outside the catalogue, we hesitate. Not because the evidence is weak, but because we are. We prefer coincidence to confrontation. We tell ourselves that everything can be explained by natural laws, forgetting that those laws themselves are still maps, not the territory. And yet there is beauty in that hesitation. The same species that once mistook meteors for divine messages now deciphers the molecular whispers of objects from other stars. Whether 3I Atlas is an enigma or merely a teacher of humility, its light has already reminded us that science is a dialogue, not a monologue, and that sometimes the universe answers in accents we've never heard before. In the coming weeks, as it swung closer to the sun, that whisper of nickel and carbon monoxide would fade, drowned by the noise of dust and radiation. But for a brief moment the spectrum had spoken clearly, a tone out of place in the cosmic symphony, both familiar and impossibly foreign. And those who heard it could not unhear it. Statistics against chance. If the universe had a casino, it would be vast, silent, and mercilessly fair. Its dice are made of gravity, its cards of probability. And when 3 Atlas rolled through our solar system, it seemed to hit double sixes again and again, too many times for comfort. Avi Loeb, the Harvard astrophysicist who first made headlines for suggesting that Oumuamua might not have been purely natural, looked at the numbers and frowned. He wasn't speculating about aliens. He was looking at compound improbabilities, a sequence of coincidences so neat that even the most cautious statistician would blink. First came the orbital alignment. The solar system is a flat disk. All 8 planets orbit roughly along the same geometric plane, like dancers circling a fire on the same invisible stage. Interstellar visitors, however, should cut across that stage at wild angles. They come from everywhere, the galactic north, the empty halo, the deep cold between the stars. Randomness predicts chaos. Yet, 3I Atlas arrived almost perfectly aligned with the planetary plane tilted by only 5 degrees, as though it had studied the choreography and decided to match it. Loeb calculated the odds roughly 1 in 500. Not impossible, but enough to raise an eyebrow. Then came the planetary flybys, Venus, Mars, Jupiter, 3 worlds each on their own long, slow orbits around the Sun, each rarely in just the right place at just the right moment. Yet, 3 key Atlas's path threaded between them with uncanny precision. It didn't collide or even graze them, but it passed close enough that from a mathematical standpoint you could call it a cosmic near-miss 3 times in a row. Each encounter on its own could be coincidence. Combine them and the odds plummet. Loeb's team estimated a probability of about 1 in 20,000 that an object from interstellar space following a random trajectory would line up to sweep through those planetary orbits in that sequence and timing. Add one more coincidence, the perihelion timing the object's moment of closest approach, occurring precisely when Earth was on the far side of the Sun, rendering it completely unobservable. The chance of that alignment, Perhaps 1 in 30. Multiply the 3 together: orbital, alignment, planetary threading, and the blind perihelion, and you get odds approaching 1 in hundreds of millions. Now, 1 in hundreds of millions isn't impossible. But it's the kind of probability that makes scientists pause and ask, how many double sixes are we comfortable calling coincidence? Imagine standing at a roulette table watching the ball land on the same number 10 times in a row. You wouldn't necessarily cry foul, but you'd start watching the wheel very closely. That's where astronomy finds itself now, in the tension between randomness and pattern. Because if 3i Atlas is natural, it is a spectacularly lucky throw of the cosmic dice. If it's not, then we're staring at design not proof of intelligence perhaps, but of something that nudges statistics into symmetry. Astronomy has been here before. In the 1700s, Edmund Halley noticed that a bright comet appeared in 1531, 1607, and 1682 every 76 years. The idea that it could be the same object returning predictably through space was outrageous at the time. Comets were omens, not clockwork. Yet Halley trusted the math of orbits predicted its return in 1758 and changed the way humanity saw the heavens forever. 2 centuries later, in 1967, a graduate student named Jocelyn Bell recorded a repeating radio signal pulsing every 1.33 seconds. It was so regular that her advisor jokingly labelled it LGM1, Little Green Men 1. For months she suspected malfunction, interference, anything but what it turned out to be the first detection of a pulsar, a rapidly rotating neutron star broadcasting cosmic heartbeats with mechanical precision. What seemed impossible coincidence, a signal too regular for nature, became proof of a new kind of star. History suggests that when probability breaks our expectations, it's usually because nature is doing something we haven't yet imagined. But occasionally, very occasionally, it's because something else is at play. That's what Loeb argues, not that 3i Atlas is artificial, but that its pattern of improbabilities demands attention. If someone rolls double sixes 10 times in a row, he said, you don't assume the dice are fair, you examine them, and perhaps that's the lesson. The universe doesn't cheat, but it does surprise. The improbable happens every day somewhere. A supernova detonates in a neighbouring galaxy. 2 black holes merge in a perfect spiral. A comet from another star just happens to cross our sky while Earth is awake to see it. Yet when the coincidences cluster, when every outcome lines up to hide the object from our view and tease our curiosity, it's hard not to wonder whether we're watching randomness or choreography disguised as chance. Maybe 3i Atlas is nature's way of reminding us that coincidence and causality are not enemies, they're dance partners. The universe rolls its dice, yes, but the table is tilted by gravity, by time, by every law we've ever discovered and many we haven't. And somewhere beneath the calculations and the probabilities, a quiet question hums. If the odds against coincidence grow large enough, does that mean the universe is trying to tell us something, or that we simply haven't learned to read its mathematics as poetry yet? The mass that refused to move. In September 2025, a quiet preprint appeared on the Open Access Library, where the future of science often arrives before peer review catches up. The title was dry enough to hide its implications. Revised Mass and Kinematic Model for Interstellar Object 3i Atlas. Buried within its tables and equations was a single number that changed the conversation. 3.3x 1010 metric tons, 33 billion tons. To anyone outside astronomy, that figure might not mean much. But to those who track the whispers of light across the solar system, it was staggering. It meant that 3i Atlas was massive, hundreds of times heavier than the object's faint glow had implied. It also meant that every hypothesis built on the assumption of a lightweight comet-like body had to be re-examined. The paper's logic was straightforward. Over months of observation, astronomers had noticed that 3i Atlas did not quite behave as gravity alone predicted. Its path curved ever so slightly, as if nudged by a tiny continuous hand. In comets, such non-gravitational accelerations are expected. Sunlight heats volatile ices, which vent gas like miniature thrusters, pushing the comet's nucleus off course by measurable degrees. But this time the numbers didn't fit. To explain the observed deviation, the amount of outgassing required would have produced a visible plume, one that simply wasn't there. Conversely, if you assumed the faint gas tail we did see was all there was, then the object's acceleration made no sense unless it was tremendously heavy. So heavy that the sublimating jets were as futile as trying to push an aircraft carrier across a harbour with a garden hose. That image, simple, absurd and vivid, spread through the astronomy community like an inside joke with an aftertaste of unease. A garden hose can spray with impressive force, so can a comet venting gas into space. But when the object in question weighs billions of tons, the math is merciless. The recoil from escaping gas would be microscopic, far too weak to alter a trajectory by even a fraction of what telescopes observed. Yet alter it did. Something didn't add up. So the researchers inverted the equation. If the motion was real and if no invisible propulsion was at play, then perhaps the mass estimate was wrong, not smaller but larger. Much larger. The team accounted for radiation pressure, solar wind drag, and even subtle gravitational tugs from Jupiter and Saturn. None of them explained the deviation. Only an enormous internal mass, dense, rigid, unyielding, made the equations balance. 33 billion tons. That's roughly half the mass of Mount Everest. It's also about the combined weight of every ship ever built by humanity. The idea that an interstellar traveler could be that heavy and still display a light vaporous tail was paradoxical. Comets are supposed to be dirty snowballs, porous, brittle, the consistency of compressed ash. Yet this thing moved like iron and shone like mist. Loeb's team framed the puzzle delicately. Either 3I Atlas possessed unusual material strength, or something about its interior was not what we assumed. Perhaps hollow, perhaps layered, perhaps something more complex. But the word they avoided deliberately cautiously was constructed, and yet the metaphor lingered. Mass in physics is resistance to acceleration and object's stubborn refusal to change its state of motion. The heavier something is, the more it demands effort to move, the more it insists on staying exactly as it is. It's a principle that shapes everything from the orbits of planets to the recoil of a pistol. But mass is also a metaphor for belief. Humanity too has inertia. We cling to what we know, to familiar explanations resisting change, until the evidence becomes irresistible. The heavier the assumption, the harder it is to move. Scientists are not immune to that inertia. They are trained skeptics. Their job is to resist premature conclusions. But there comes a moment when resistance itself begins to distort the orbit of understanding, when clinging to what should be true prevents us from seeing what is. Perhaps that's why the September paper struck such a chord. It didn't shout speculation, it whispered data. And in that whisper was a quiet challenge if the numbers are right. Then our mental model of what a comet can be and what interstellar space might send our way needs to shift. For decades, humanity has assumed that small interstellar visitors would resemble the leftovers of planet formation fragments, ice shards, rubble. But the universe rarely respects our expectations. It builds mountains that float black holes that evaporate, and now apparently visitors whose mass resists not only solar radiation, but our willingness to categorize. At its core, the September discovery was a reminder that physics and philosophy often share a boundary, the line between what moves and what refuses to. Matter resists acceleration, minds resist astonishment, and sometimes both must be overcome for truth to move at all. So the object continues on indifferent to our curiosity, bending ever so slightly against the sun's pull, as if to prove that even in a universe ruled by gravity, some things have a will of their own. A mountain among pebbles. In nature, size obeys a quiet rule, a law so pervasive it seems almost sacred. It's called a power law distribution, and it governs everything from the craters on the moon to the earthquakes beneath our feet. Simply put, the big things are rare and the small things are countless. For every towering mountain there are thousands of hills. For every magnitude 8 earthquake, millions of tremors pass unnoticed. The universe, like an impartial accountant, favors the modest. It spends its energy frugally scattering the cosmos with small events and saving the grand ones for the rarest occasions. Astronomers see this same law everywhere they look. In the asteroid belt, kilometer-wide, boulders outnumber 100-kilometer asteroids by millions. Among stars, tiny red dwarfs are abundant, while giants are exceptional. Even galaxies obey the pattern. The universe builds more dwarfs than spirals, more spirals than titans. It's a symmetry of scarcity, a kind of cosmic economy, and like all economies, it thrives on balance. So when 3I Atlas entered the record books, its size and brightness immediately stood out like a skyscraper in a village of huts. It wasn't supposed to exist in the way it does. By the math of power laws, interstellar debris should mostly be dust gravel and the occasional rock the size of a truck. We should be sweeping up trillions of tiny messengers from other systems, long before encountering a single object tens of kilometers wide and billions of tons heavy. But the sky has delivered the opposite. In 2017 came Oumuamua, elongated, reflective and oddly light, perhaps no larger than a football field. Then in 2019, 2i Borisov, a normal comet-sized visitor, small expected fleeting. But now with 3i Atlas, the trend has flipped an object 30 times larger, hundreds of times heavier, and far more chemically complex than probability suggests we should ever see. It's like digging in a sandbox expecting pebbles and striking a mountain instead. Statistically, the universe doesn't roll dice like this. The odds of 3 interstellar visitors in less than a decade, one anomalous, one ordinary, and one impossibly massive break every expectation of how interstellar objects should be distributed. Either the universe is dramatically more productive at ejecting giants than we thought, or we've stumbled upon something that doesn't fit nature's pattern at all. To grasp the improbability, it helps to think closer to home. City sizes follow the same power law. There are countless small towns, fewer mid-sized cities, and only a handful of sprawling megacities. Imagine visiting a new continent and finding that every settlement you see is the size of New York or Tokyo, with no small towns at all. You would suspect something artificial planning selection intent. The same is true for wealth. In every economy, millions live modestly while a rare few hold immense fortune. A sudden cluster of billionaires appearing in a village would raise questions about coincidence versus cause. Or take earthquakes. The vast majority never reach human notice. Only once in years does the crust release energy powerful enough to shatter skylines. Now imagine 3 such events, each stronger than the last, striking the same region in quick succession. The statisticians would not call it random, they'd look for hidden connections, unseen stresses. That's the scale of the anomaly 3i Atlas represents. The physics of planet formation, the dynamics of stellar systems, even the gravitational billiards of galactic drift all point toward one conclusion. Large interstellar bodies should be exceedingly rare. Yet we have found one with a mass approaching the unimaginable, following an improbably precise path, wrapped in chemistry that seems to defy both nature and probability. Avi Loeb calls it a statistical outlier among outliers. Others prefer a softer phrase, an exception that tests the rule. But every rule that meets its exception must eventually bend or break. So scientists now face a quiet heresy, the thought that perhaps nature occasionally cheats its own statistics. Maybe the universe isn't bound by our neat curves and distributions. Maybe there are regions, stellar nurseries, ancient civilizations, or long-dead planetary foundries that churn out anomalies by design, not accident. The power law, after all, is a human observation, not a commandment of physics. It describes what we've seen, not all that can be. Like the tide tables of old sailors, it works until one day the ocean behaves differently. 3i Atlas is that rogue tide. Its size alone forces us to ask an uncomfortable question when a pattern so universal suddenly fails. Do we question the universe or the limits of our imagination? For now, the object glides onward indifferent to our surprise, a mountain adrift among pebbles, silently rewriting the statistics of everything we thought we knew, the shape of impossibility. Every orbit hides a secret, but sometimes the secret isn't in the path, it's in the shape. When the September data on 3i Atlas mass went public, astronomers began to calculate its density, the simple ratio between weight and volume. Density tells us whether something is rock ice metal or something stranger. It's the same calculation that lets scientists infer that Saturn could float in water, or that the moon's core must be small and iron-rich. For 3i Atlas, the numbers made no sense. If it truly weighed 33 billion tons, yet reflected sunlight as faintly as a comet of ordinary brightness, its bulk had to be far larger than expected. But when you divided that mass by its observed size, you didn't get the density of rock or ice, you got something far lighter, almost absurdly so. It was as if a mountain had the weight of a snowdrift. One astrophysicist speaking off record called it a hollow cathedral of stone. It wasn't just poetic exaggeration. The math implied a void ratio empty space within that bordered on the impossible. A natural comet, even a porous one, might have 30 to 60% void. 3i Atlas seemed to exceed 90. It was too light to be solid, too stable to be fragile. If a fragmentary rubble pile had that much emptiness, it would have disintegrated long before entering the inner solar system. Yet this object held its form while enduring solar radiation, intense enough to peel molecules from its skin. How could something so hollow be so durable? One possibility raised reluctantly was geometry. Nature can build strength from emptiness. Snowflakes, bones, and honeycombs are living proof lattices where structure triumphs over mass. Engineers call this distributed rigidity, A bridge built from trusses can bear enormous loads with minimal material. A spacecraft made from carbon composites can resist pressure while remaining feather-light. So imagine purely as thought experiment that someone somewhere wanted to send an artifact across interstellar space, not for decades, but for millennia. Weight would be the enemy, longevity, the goal. You'd build not a boulder, but a shell lightweight hollow, perhaps spinning slowly for stability. You'd armor it in carbon or nickel to survive micrometeoroids, then let it drift conserving momentum, silent as a seed waiting for sunlight. In other words, it would look exactly like a comet. That's the uncomfortable symmetry between artifice and nature-convergent design. When the environment demands survival, even intelligence and randomness arrive at similar solutions. Streamlined fish and submarines share the same hydrodynamics. Bird wings and airplane wings obey the same equations of lift. So if an ancient civilization long vanished once built something to cross the void, its engineers might have discovered what comets already know, that strength can be hidden in hollowness. Of course, this remains speculation, a fragile bridge built from coincidence. No one in the scientific community has declared 3i Atlas artificial, but the mere possibility has reawakened a philosophical question that science rarely voices aloud. At what point does imitation become indistinguishable from authenticity? If an artifact perfectly mimics a natural form, follows the same orbit, the same chemistry, the same surface erosion, how would we ever tell? The cosmos is a patient sculptor. Given enough time, even machines would weather into stone. 1 billion years of cosmic dust and ultraviolet radiation could turn a hull into a rock, a reactor into a frozen core. The difference between made and born might erode until only pattern remains, and pattern is a language the universe speaks fluently. Perhaps that's why so many hesitate to draw conclusions. Because if 3 Atlas is artificial, it tells us something staggering about whoever made it. But if it's natural, it tells us something even more staggering, that blind physics, unaided by thought, can produce a shape so elegant it mirrors intention. We like to believe purpose is what separates design from accident, but nature blurs the line every day. Snowflakes build perfect symmetry without a single thought. Galaxies spiral like fingerprints with no architect. Coral reefs construct cathedrals beneath the waves without knowing the word architecture. Maybe that's what 3i Atlas is, a reminder that imitation works both ways. Our machines mimic nature, and perhaps nature occasionally mimics us. In the end, we're left with an equation that refuses to close. If it's hollow, it shouldn't survive. If it's solid, it shouldn't weigh so little. Between those contradictions, a quiet mystery spins, neither artifact nor accident, just a shape that disobeys expectation. And maybe that's the truest definition of wonder. Not what we can explain, but what refuses to fit the categories we built to contain it. The trajectory that threads the planets. If one could paint its journey across the solar system, 3 Atlas would trace a line so delicate, so improbably threaded through the planetary orbits, that even the most seasoned navigator would call it art. It entered from the north, descending toward the ecliptic like a silent diver approaching the surface of a vast sunlit sea. Every planet moves within that thin glowing plane, a sheet of invisible geometry, where the sun's gravity writes its most intricate choreography. To arrive at just the right inclination to slip into that narrow corridor among billions of cubic miles of void is already rare, but to cross it through the exact neighborhoods of 4 major planets in sequence Mars, Venus, Earth and Jupiter without collision or deflection, that's something the universe does once in many millennia, if ever. Astronomers plotted the path on digital maps that looked almost too graceful to be real. The line began far beyond Neptune, curved inward across the solar plane, and wove between worlds as though guided by an unseen hand. The precision was breathtaking, a pass near Mars within a few tens of thousands of kilometers, a near alignment with Earth's orbital track close enough that had it arrived just weeks earlier, it might have passed within lunar distance. Then a gentle drift inward toward Venus, before curving outward toward Jupiter, grazing the giant's gravitational field like a fingertip across the edge of a harp string. Each encounter shifted its motion by the smallest of degrees, as though space itself were tuning it. Every gravitational field, Mars' subtle tug, Venus's dense pull, Jupiter's monumental reach altered the trajectory fraction by fraction, not enough to trap it, but just enough to keep it aligned. The odds of such threading occurring by accident are microscopic. Astronomers ran simulations, tens of thousands of randomized entries into the solar system from interstellar space. Only a handful passed within even 2 planetary neighborhoods. Fewer than 1 in 100,000 achieved the fourfold path 3i Atlas followed. It was as if nature had recreated by coincidence what humanity once accomplished by design the Voyager Grand Tour. In 1977, NASA launched Voyagers 1 and 2 to take advantage of a rare alignment of the outer planets, a window that occurs only once every 176 years. The spacecraft used gravity itself as a slingshot, borrowing speed from Jupiter, then Saturn, then Uranus and Neptune to leap from world to world without expending fuel. The alignment was so specific, so mathematically narrow, that engineers said it was like threading a needle with the universe. 3i Atlas seems to be performing a similar feat, only backward and blind, a natural object following a path as elegant as our most deliberate engineering. That's what unsettles the statisticians. The Voyager Grand Tour required decades of planning an entire civilization of mathematicians, engineers, and computers. 3 Atlas, by contrast, is a fragment of something unknown, and yet it's moving through the same cosmic ballet as if it too had read the choreography. Perhaps it's pure chance. Perhaps the solar system, like any casino, occasionally allows a perfect run of luck. But the longer one stares at the map of its path, the less it feels random, and the more it feels inevitable, as though the universe had set the pieces long ago waiting for this single move to complete the pattern. From Mars' thin red shadow, to Venus's gleaming clouds, from Earth's orbit where humanity watches in wonder, to Jupiter's immense magnetic field, 3i Atlas passes like a silent observer through the clockwork of our celestial system, untouched, unanswering, utterly precise. To visualize it is to feel awe of a different kind. Imagine the solar system as a great mechanical orrery, each planet a gear turning at its appointed pace. Then from the darkness beyond the outer rim, a tiny spark arcs inward and impossibly meshes with every gear at once, gliding through the system, without collision, without error, before slipping back into the dark. That is 3i Atlas, a visitor tracing perfection through motion like a signature written in gravity. It will never return. Its path once complete will open again into interstellar space, never repeating, never closing. But for this brief moment, this one golden alignment spanning from Mars to Jupiter, it moves in harmony with everything we've ever known, as if to remind us that even in the vast indifference of the cosmos, coincidence can sometimes masquerade as design. And somewhere deep inside that symmetry between accident and intention lies the quiet question that defines our species. Do we see patterns because they exist, or because we need them to? For now, 3i Atlas glides onward, its invisible thread still taut across the solar plane, the voyager of no one, the traveller without a home moving through a corridor only the universe itself could have drawn. The casino of the cosmos, the universe. When you think about it, runs the strangest casino imaginable. Its tables are made of gravity wells, its dice carved from hydrogen and chance. Every photon that strikes a telescope's mirror is the roll of that dice, a random outcome written in light. And yet amid all this chaos we keep finding patterns that feel too perfect, too deliberate. Avi Loeb once described it simply, 3i Atlas is the cosmic equivalent of rolling double sixes again and again. He wasn't being poetic. He was pointing out the statistical impossibility of what we were seeing, the alignment of orbits, the timing of perihelion, the chemical anomalies, the precise threading of planets. One improbable event can be dismissed. 2 might raise an eyebrow. But when improbabilities pile up, the human mind does what it has always done. It starts to whisper that perhaps the dice are loaded. That whisper is both our greatest strength and our oldest trap. We are pattern-seeking creatures. Our ancestors survived by recognizing the faintest rhythm in the chaos, the direction of migrating herds, the turn of the seasons, the shape of a predator's shadow in tall grass. Pattern recognition is our evolutionary inheritance, the seed of both science and superstition. It built telescopes and temples alike. So when we stare into space and see coincidence after coincidence, an interstellar visitor choosing by chance the very path we were designed for a probe, aligning with the planetary plane like an obedient guest, vanishing behind the sun at the exact moment of closest scrutiny, that ancient instinct stirs again. It tells us this means something. But does it? Statisticians will tell you that improbable things happen all the time. Roll a pair of dice long enough and you'll get double sixes 10 times in a row eventually, if you wait through a few trillion throws. The problem is we rarely witness the trillions. We see only the miracle in front of us and forget the infinity of mundane roles that came before. Loeb's analogy cuts both ways. Double sixes feel significant only because they stand out. To the dice, every roll is equal. To us, meaning emerges in contrast. That's the heart of our confusion with 3i Atlas, not whether it is natural or designed, but whether meaning itself is intrinsic or projected. When a coincidence feels too perfect, the rational mind wavers between skepticism and wonder, torn between the comfort of randomness and the thrill of purpose. Science tries to navigate that razor's edge. Its discipline is to say coincidence until proven otherwise. But its spirit, the one that drives telescopes and risk and sleepless nights, is to ask, what if it's not? This duality defines us. Skepticism keeps us grounded, wonder keeps us reaching. Too much skepticism and the world becomes flat and silent. Too much wonder and we fall into myth. The art of science is the balance believing neither too much nor too little, holding uncertainty like a compass that never stops quivering. And so the casino metaphor becomes more than statistics, it becomes a mirror. Because in truth, we're not just watching the dice roll, we're part of the game. The patterns we perceive are shaped by the very minds that look for them. Our questions bend the probabilities simply by existing. Somewhere between psychology and physics lies a strange frontier, the point where coincidence feels like communication. Ancient civilizations called it divination. Today we call it data analysis. But the feeling hasn't changed that electric sense that the universe might be winking back. So when does pattern recognition become revelation? Perhaps when enough coincidences stop being coincidences in the story we tell ourselves. Perhaps when we decide that the role of double sixes isn't luck, but invitation. The truth as always lies in motion, in the willingness to keep rolling, keep observing, keep asking, without collapsing wonder into certainty. Because in the casino of the cosmos, every observation is a bet against ignorance. The stakes are not money, but meaning. And sometimes the reward for curiosity is not the jackpot of proof, but the quiet astonishment that the dice rolled at all. 3i Atlas. Meanwhile continues its streak, silent, distant, unbothered by our odds. The universe plays on, and we keep counting the throws, hoping that somewhere in the pattern of chance revelation still waits for us. The 3 weeks of darkness. For 21 days the universe will close its eyelid. That is how astronomers describe it, half jokingly, half reverently, the solar conjunction of 3 Atlas. From October 29 to November 19th, 2025, the object will slip behind the Sun, as seen from Earth, hidden in a glare so intense that no telescope, no camera, no spacecraft can follow. It will be as though the cosmos itself has drawn a curtain, blotting out the very thing we wish most to see. In technical terms, it's simple geometry. Earth orbits one side of the Sun. 3i Atlas, hurtling inward on its hyperbolic path, passes behind it on the opposite side. The line of sight is lost. The Sun, 10.4 million kilometers wide, sits between us and the mystery. Even instruments in space like the James Webb Telescope orbiting at L2 or the Parker Solar Probe cannot look directly through that blinding center. The Sun's corona is too fierce, its radiation too saturating. To aim a telescope that close to the solar disk is to risk burning its sensors to white noise. So we wait. The last time we saw 3i Atlas, clearly it was brightening its coma, expanding in a pale green haze of carbon gas. Then day by day the light began to fade, not because the object dimmed, but because the Sun's brilliance swallowed it whole. Soon even the most powerful instruments reported only noise. The data streams turned blank. Silence. For scientists, this is the loneliest kind of blindness. Observation is the heartbeat of knowledge. Without it, even the most rigorous equations become speculation. When a spacecraft disappears behind a planet, we know it will re-emerge. But when an interstellar visitor hides behind the Sun, there's an unspoken anxiety. What if it doesn't return? The same astronomers have watched comets vanish into the solar corona before only to see them fragment, dissolve, or simply never come back. The Sun is both giver and destroyer, its heat revealing and erasing in the same breath. Every orbit that strays too close risks annihilation. Yet there's something profoundly human in this pause. All over Earth, observatories have marked the dates in their schedules, no data object behind Sun. It reads like a collective sigh written into the calendar of the species. For 3 weeks, the world's eyes will be blind to its most tantalizing mystery. Imagine it cinematically, the solar system, as a vast stage of light and shadow, every planet circling in its predictable rhythm. And then from beyond the outer dark, enters a visitor, a wanderer from another star crossing that stage just long enough for humanity to notice. We lean forward, straining to see its face, and at the crucial moment the spotlight flares too bright. The stage vanishes in brilliance. The play continues behind the curtain unseen. That's what October 29th will be the beginning of an intermission written by the Sun. Solar conjunctions have frustrated space science for decades. During Mars missions, engineers suspend communication for fear of radio interference. Solar plasma scatters signals, corrupting bits of data until they sound like static whispers. Even light itself is deflected by the Sun's gravity-bending trajectories and blurring sight lines. And so, like ancient skywatchers waiting for an eclipse to pass, modern scientists must surrender to darkness. They can only predict, model, and hope. On their monitors, numbers replace images, orbital elements, probabilities, timestamps. And yet behind those abstractions pulses an almost spiritual tension. Because everyone knows what's really happening. Somewhere beyond that furnace, 3i Atlas is enduring the trial of light. Its surface is boiling. Its gases are venting into a shimmering tail that no one can see. Inside that blinding silence, it may be splitting apart or holding together with impossible grace. It's an ordeal no human can witness, only imagine. And that imagination in the absence of sight becomes vivid. Artists begin to render what instruments cannot. A silhouette crossing the corona, a faint glimmer of green, a contrail of dust drawn across the golden halo of the sun. In the darkened control rooms of observatories, those images circulate like prayers disguised as pixels. The human mind cannot tolerate a blank sky. Where light ends, story begins. We tell ourselves that when the object emerges again in late November, it will bring answers, that the veil will lift and we will see whether it survived. But part of us quietly, almost guiltily, hopes it changes, that something new will come out of the sun's shadow, altered by a passage no human eye could witness. Because that is what we secretly expect of mystery, not explanation, but transformation. For now, the countdown to darkness continues. The last telescopic images are archived. The data pipelines go quiet. Across observatories, engineers shut their domes and step outside into the night, where the stars still burn in patient silence. They look toward the sun's position, blinding unreachable, and imagine the traveller on the far side, wrapped in light unseen but still moving. The universe has blinked. We who have made a profession of watching must learn again how to wait. The possibility of a maneuver. Every spacecraft engineer knows there is one moment when motion itself becomes magnified, a point in an orbit where a small push can alter destiny. It's called the Oberth effect, named after the German physicist Hermann Oberth, one of the visionaries who imagined spaceflight long before it became real. In essence, it's simple but profound. When a vessel moves fastest at perihelion, the moment of closest approach to the sun, its engines, if fired, then gain far more from the same burn than they would anywhere else. The logic is pure physics. Kinetic energy scales with velocity squared. The faster you move, the greater the payoff of every drop of thrust. A rocket igniting near the sun gains a kind of gravitational dividend. What would be a gentle nudge in deep space becomes a slingshot multiplying speed or bending trajectory with minimal fuel. It's why interplanetary probes like Parker and Solar Orbiter make their course corrections there. And it's why if someone or something wanted to alter its path without being seen, that fiery moment behind the sun would be the ideal curtain. Astronomers can model 3i Atlas's orbit with exquisite precision, up to the point it vanished into the solar glare. Every parameter, eccentricity, inclination, perihelion distance was known. But once it crossed behind the sun, observation ceased. For those 3 weeks, any change in its speed or direction would be invisible. By the time it re-emerged days later, its new trajectory would appear as a natural continuation, unless someone was specifically searching for an anomaly in the math. That is the haunting beauty and danger of the Oberth effect. It makes nature itself complicit in disguise. During the Cold War, humanity learned that lesson well. The early years of orbital espionage were built on moments when physics could hide intention. Soviet and American satellites performed tiny precise burns on the far side of Earth, their engines flaring for seconds unseen by radar. Each maneuver altered the geometry of surveillance, changed fields of view, shifted orbits ever so slightly to avoid detection. Even the moon once served as a shield, communications relayed behind its bulk to mask secret transmissions. In that era, invisibility was strategy. Today, it is speculation. The idea that an interstellar object might use the same trick feels almost absurd, and yet from a strictly physical standpoint, this would be the time to do it. The sun's gravity offers not only concealment, but opportunity. A well-timed release of gas or controlled thrust, even the tiniest impulse could shift 3I Atlas from an open hyperbolic path destined to leave the solar system forever into a bound elliptical orbit captured by the sun perhaps for centuries. That transition, if it occurred, would be subtle. The object wouldn't suddenly break or glow. It would simply adjust its speed by a fraction, a whisper of change in velocity that only a reappearance months later could reveal. A comet that should have left the stage might still linger in the wings, circling quietly among the inner planets. Is that what's happening now? No one can say. But the geometry invites the question. Avi Loeb once wrote that the absence of evidence is not evidence of absence, only the geometry of ignorance. His words apply perfectly here. The blind spot behind the sun is not just a patch of unobservable space, it's a window of plausible deniability. Anything could happen there and physics would politely conceal it. If a civilization or an autonomous probe wanted to perform an orbital capture, it wouldn't need vast energy-only timing. A simple outgassing valve, a thermal jet, a solar sail adjustment could suffice. With no one watching, no instrument recording their act would vanish into light, the universe's most forgiving camouflage. Even among scientists, the notion provokes a hush. Not because they suspect malice, but because they recognize elegance. A maneuver at perihelion would exploit the oldest law of celestial mechanics to achieve the newest kind of secrecy. It would be a message written not in radio waves, but in silence and trajectory. But perhaps the more unsettling parallel isn't technological, it's psychological. Humans too perform their course corrections in the heat of pressure. We change direction when we're closest to the fire at the crisis points, when the energy of life burns hottest. We make our quiet maneuvers in secrecy, adjusting paths unseen by others, hoping to emerge from the glare with trajectories that still make sense. That's why the idea of 3I Atlas executing a hidden change stirs something beyond curiosity. It feels familiar. It mirrors our own instinct to alter fate while pretending nothing has changed. In a few weeks, the object will reappear. If its path is unaltered, we will call it coincidence natural as comet dust. But if its speed or angle differs by even a fraction, astronomers will scramble to explain it. Solar wind jets, measurement error, anything but intention. Because intention would mean awareness. An awareness in the vast indifference of the cosmos would mean we are not the only ones who understand the value of a well-timed maneuver. Until then, the sun keeps its secret. Behind its white brilliance, an object older than our species may be bending its path invisible to every eye on Earth. And as humanity watches the glare in silence, perhaps the universe is performing the oldest sleight of hand hiding change inside light itself. When Hubble blinked on July 21, 2025, the Hubble Space Telescope fixed its unblinking gaze on 3I Atlas. At first, the images looked routine, a soft halo of dust around a glowing nucleus, a faint tail sweeping away from the sun. But then came the detail that made astronomers pause, a thin streak of light pointing the wrong way. It wasn't trailing the object as comets usually do. It was facing forward toward the sun, a counterintuitive gesture like a kite flying into the wind. NASA released the images with careful language, not alarm, not excitement. Just the neutral phrasing of scientists who know the danger of adjectives. They explained it as an imaging artifact, the ghost of motion in a long exposure. When photographing something millions of miles away, Hubble must track it across the sky. If the timing isn't perfect, if the target moves even slightly during exposure, light can smear into strange geometries. The comet's rapid motion relative to background stars can make it appear as if the tail, which should trail away, extends forward instead. To most professionals, the explanation fit. Motion blur sends adrift, scattering familiar ghosts that haunt astronomical imaging. But to others, it raised an uneasy question. How often have history's discoveries begun as artifacts? In 1967, Jocelyn Bell noticed a peculiar pattern of pulses in her radio data. She called it LGM-1 for Little Green Men Half in Jest. It too was nearly dismissed as an artifact before it became the first confirmed pulsar. The line between error and revelation, it seems, is drawn only after enough people agree on which side the mystery belongs, and so Hubble's forward-facing tail became another entry in that fragile catalogue of almost the optical mirages that may either precede discovery or fade into noise. By August, fresh data arrived from Chile's Gemini South telescope. The southern skies were clear and the object brighter than before. In those images, the anomaly was gone. The tail streamed neatly away from the sun, its coma symmetrical, its behavior comfortingly ordinary. Nothing unusual, the summary read. The forward streak, everyone agreed, had been an illusion after all, but the illusion lingered not on the sensors but in the minds of those who study them. Because when Hubble blinks, the world remembers. The telescope's eye is supposed to be infallible, no atmosphere, no clouds, no sleep. Yet even perfection has thresholds. Cosmic rays strike the detectors. Electronic noise mimics structure. The faintest vibration in orbit can translate into distortions measured in millionths of a pixel. In that fragility lies the most human truth of all science, that every image we capture of the universe is filtered through the trembling of our own instruments. Still, scientists pressed on cataloguing spectra, comparing brightness curves, measuring how the coma changed as 3i Atlas approached the sun. Every result looked increasingly normal. The mystery, if one remained, was subtle, perhaps psychological more than physical. Why had the brief flicker of ambiguity caused such disproportionate fascination? Because uncertainty is intoxicating. For a moment, when that forward streak appeared, the cosmos felt alive with possibility again. A camera had blinked and the entire planet held its breath. Was it motion blur or motion of a different kind? When the Gemini results came, most felt relief. The natural order had been restored. The equations still held. Hubble, that aging sentinel of low Earth orbit, had merely seen the universe in double, for a moment a slip of vision, not revelation. But others felt a quieter emotion, humility. Because what if that is the nature of all our seeing? What if every observation from Galileo's first telescope to Webb's deep field is only a blink between two states of not knowing? For all its confidence, modern astronomy is still a language of translation. Light becomes data, data becomes meaning, and meaning always risks distortion. A tiny artifact can masquerade as significance. A true anomaly can vanish under the label of error. In that fragile space between artifact and anomaly, humanity continues to search for truth. When Hubble blinked, it reminded us that our instruments are extensions of our own perception, brilliant but fallible, precise yet profoundly human. And so the forward-facing tail was filed away as a curiosity, a quirk of timing and optics. Officially resolved, unofficially unresolved. Because somewhere in that temporary confusion we glimpsed a deeper paradox. The more advanced our eyes become, the more we realize how much of the universe still hides behind them. In the end, humility may be the most valuable data point we ever collect. Every photograph, every line of code, every spectrum from 3i Atlas is a reminder that to observe is to interpret, and to interpret is to risk being wrong. But that risk, that trembling line between clarity and illusion, is where discovery lives. And so, when Hubble blinked, perhaps the universe wasn't mocking us. Perhaps it was teaching us how to see again. The chemical whispers of another world, every comet carries a voice not one of sound, but of light. Split through a spectroscope, that light becomes a pattern of colours and lines, each one an atomic syllable spelling out the story of where it was born. Astronomers call it spectral fingerprinting. But to the poetic mind it is more intimate, a whisper from matter itself, billions of years old, crossing the void to be heard by beings who have only just learned to listen. When 3 Atlas first began to glow under the sun's heat, telescopes across the world turned their instruments to catch those whispers. What they found did not match the dialect of ordinary comets. Instead of water vapour dominating the voice, it was carbon dioxide released at nearly 8 times the rate of H2O. That ratio mattered. In our solar system, comets are mostly made of frozen water. The famous CE-67P Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta, and Philae Landers was roughly 80% water ice by volume. Its CO2 emissions were small transient, the breath of a body, shaped in the warmer middle zones of our solar nebula. Thyrsis Atlas, by contrast, seemed forged in a place far colder, where even carbon dioxide could freeze solid and remain trapped for eons, a cradle so distant from its star that sunlight was only a rumour. And then came the stranger finding nickel vapour without iron. Using the Very Large Telescope in Chile, scientists detected nickel tetracarbonyl, a compound of nickel and carbon monoxide bleeding from the comet's surface at about 4.6 grams per second. Normally, nickel and iron travel together, twins born in the heart of supernovae scattered into the same cosmic nurseries. To find one without the other is like discovering a fingerprint missing half its ridges possible, but deeply unsettling. Comet 67P showed the expected balanced nickel and iron released in comparable quantities, their spectral lines rising together like harmonized notes in a song older than the planets. But in 3 Atlas, only nickel sings, the iron line silent. There are theories, of course. Perhaps the iron is trapped in compounds too stable to vaporize. Perhaps our instruments, still straining to catch light from billions of miles away, simply aren't sensitive enough. Or perhaps, and this is where science trembles into imagination, the object formed in a region of its parent system where elemental abundances were different, where supernova yields seeded space unevenly, where chemistry itself followed rules unlike those that sculpted our sun. To trace those differences is to trace time itself. Every atom of nickel, every molecule of carbon dioxide is a breadcrumb from the dawn of some distant world. Their ratios tell us about the temperature of that birthplace, the radiation of its star, the density of the cloud from which it condensed. To measure them is to listen backward through cosmic history, to read in chemistry the echoes of creation. If we could follow those isotopic clues to their source, we might identify the very kind of star that once warmed 3 Atlas. Maybe a red dwarf faint and long-lived. Maybe a binary pair whose dance sculpted the protoplanetary dust in strange ways. Or perhaps more poetically, a sun that no longer exists, its memory carried forward in molecules that outlasted its light. Astronomers, in their caution, call such inferences chemical evolution models. Yet behind the formulas lies wonder that the composition of a single grain of dust can tell us not only where it came from, but what the universe was doing at that moment. When we say 3I Atlas is rich in CO2, we are not just describing its content, we are describing the temperature of another sun's cradle 4 billion years ago. And still amid the data, something feels off. Carbon dioxide so abundant that it overshadows water. Nickel singing alone without its iron twin. Cyanide faint but rising in strength. These are the chemical fingerprints of a traveller that doesn't fit the pattern of our family's DNA. It's as if the cosmos had sent us a postcard in a language we almost understand, but the accent is wrong, the syntax uncanny. In laboratories on Earth, scientists build analogues mixtures of ice dust and metal under vacuum chambers, mimicking the birthplaces of comets. They blast them with ultraviolet light, measure the gases that evaporate. None of the simulations reproduce the precise ratios of 3I Atlas. Something is missing, or perhaps something extra. Nickel tetracarbonyl is an industrial compound on Earth so toxic that a few milligrams can poison the lungs. It was once used in the refining of metals, a ghost of human manufacture. To find it here drifting from an object older than humanity feels almost ironic, a mirror image of our own chemistry thrown back across time. As if the universe were reminding us you did not invent complexity. You merely rediscovered it. And perhaps that is the lesson hidden in its spectral lines. Every spectrum is a confession not of intent but of origin. When we decode it, we are eavesdropping on the physics of forgotten stars, on the alchemy of dust turned to destiny. Somewhere, light years away, a parent sun once shone on the ice that became 3I Atlas. It is gone now, but its chemistry endures whispering across centuries of interstellar night. We record those whispers on glass, translate them into graphs, call them data. But what they truly are memories. In the end, we may never know if the missing iron is coincidence or clue, if the carbon dioxide excess is anomaly or artifact. But in their imbalance, these elements speak. They remind us that every world, every fragment carries its own fingerprint, and that even silence when seen through a prism glows with meaning. To study 3I Atlas is to listen to the chemical whispers of another world, one we will never visit, whose star may already have died, but whose story still travels at the speed of light. Green flame in the dark. Even before the spectrometer spoke, people could see the strangeness. By late September 2025, the comet, if one can still call it that, had begun to shimmer with an emerald glow bright enough to be captured in long exposures from amateur telescopes across the world. A soft halo of green surrounded its nucleus, glowing against the black velvet of space like a lantern adrift in infinite dark. Comets often shine green. It is one of the few constants of the heavens, the colour of gas set alight by sunlight, the fluorescence of molecules called diatomic carbon and cyanide. But what puzzled scientists about 3I Atlas was that the very chemicals that should have produced that hue were largely absent. Spectroscopic analysis showed a depletion of the carbon chain molecules that normally blaze at that wavelength. In comets like 67P or Halley, those compounds dominate, breaking apart under ultraviolet radiation to emit their eerie glow. But here the expected signals were faint. Yet the light, unmistakably green, persisted, defying its own chemistry. NASA's preliminary bulletins described it as anomalous fluorescence, a phrase that could mean almost anything. The European Southern Observatory offered one hypothesis. Perhaps the cyanide bands were being excited at unusual energy levels due to an atypical solar angle or interaction with metallic carbonyls like nickel tetracarbonyl, whose breakdown can emit green-tinted spectra. Others suggested a more poetic mechanism, that the light was being refracted through a coma rich in CO2 ice crystals, filtering sunlight the way certain minerals turn white fire into colour. Whatever the cause, the glow deepened each week as the object approached the sun, as though the nearer it came to destruction, the more alive it appeared. Green. Across cultures, it is the colour of rebirth and poison of spring and warning. The Egyptians painted Osiris, god of resurrection, in green flesh. Medieval alchemists used the term viriditas, the greening power, to describe the vital energy in all living things. Yet sailors once feared green lights on the sea as omens of disaster, St. Elmo's fire dancing on mast before storms. To see that colour burning now on an interstellar visitor streaking toward the sun felt both comforting and ominous, a cosmic echo of life's duality, creation and decay, bound in the same wavelength. Some nights the green was so vivid that it bled through telescope filters. Long exposure photographs revealed tendrils curling like mist. Not the structured jets of dust typical of comets, but diffuse shifting veils that seemed almost to pulse. The longer observers stared, the more it resembled something alive. Of course, it wasn't, at least not in any biological sense, but life has always borrowed its metaphors from light. Reporters predictably seized on the colour. Headlines spoke of the emerald visitor and the green messenger from another star. The public imagination, always hungry for symbols, connected the hue to mythology, the green ray at sunset, the heart chakra, the aurora that bridges heaven and earth. Meanwhile, scientists resisted the poetry but shared the fascination. There was something about that colour that unsettled even the most rational minds, because it implied persistence. Normally a comet's green coma fades quickly as the molecules responsible are destroyed by sunlight. The reaction lasts days, sometimes hours. But 3 Atlas glowed steadily for weeks unblinking. The emission spectrum refused to decay. Even as the object rotated, even as its distance changed, the hue remained constant, not flickering, not pulsing, but unwavering, like a steady flame burning in vacuum. To the eye of science, it was a data point. To the human soul, it was a question. Avi Loeb, ever the careful provocateur, wrote an op-ed in Scientific American titled Persistent Strangeness. In it, he reminded readers that the colour green in quantum terms corresponds to photons of about 520 nanometers light, that sits exactly between the blue of ionized gases and the yellow of reflected dust. It is, he wrote, the spectral midpoint between what nature emits and what thought perceives. He meant it metaphorically, that the universe sometimes glows brightest where explanation fades. But many took the phrase literally. Persistent strangeness became shorthand for everything about 3I Atlas that refused to conform: the mass, the density, the trajectory, the hollow strength, and now the light. By November, the object would vanish behind the sun, its green fire swallowed by the greater blaze. But the images remained pixelated, ghostly luminous, archived in data centers from Pasadena to Geneva. Scientists continued to debate chemical pathways, optical scattering, and excitation bands. Yet beneath the analysis, everyone sensed that something more profound had been glimpsed, a beauty that resisted closure. Perhaps the green was nothing more than sunlight playing with molecules we don't yet understand. Or perhaps it was a message written in physics, not for us, but through us, proof that mystery can still burn bright in a universe we keep trying to measure into silence. Whatever the truth, its glow lingers. A green flame in the dark, a reminder that even in the cold equations of space, life's colour in all its ambiguity still finds a way to shine. Or as Loeb would later say with a wry smile, sometimes the universe refuses to behave. It simply insists on its own persistent strangeness. The December encounter, December the 19th, 2025. For the first time in 3 weeks, the blindfold will lift. The 3 Atlas will step out from behind the sun and earth, now tilted in its winter posture, will finally see it again. By every calculation, it will pass at 1.8 astronomical units, roughly 270 million kilometers away, close enough for our instruments to see it in exquisite detail, yet safely distant. In cosmic terms, it will brush past us as a whisper, not a wind. But for those who have spent months watching the mystery unfold, the approach feels less like distance measured in kilometers than in anticipation measured in heartbeats. Every telescope that can turn toward it will do so. The James Webb Space Telescope, peering from its cold perch at L2, has reserved time to observe 3I Atlas across infrared wavelengths. Its mirrors cooled to near absolute zero will catch photons from the object that left its surface minutes earlier, their signatures mapping dust temperatures, ice composition, and any trace of complex organics. Webb's instruments will look not for spectacle but for subtlety, the molecular fingerprints that can tell us what this traveller remembers of its home star. Meanwhile, the Hubble Space Telescope, though aging, will lend its veteran eye once more. Its ultraviolet sensors can detect the faint fluorescence of gas escaping into the void, the breath of the comet against sunlight. Engineers have already planned precise exposure sequences to avoid overexposure from the sun's lingering glare. Hubble's role will be to capture continuity to compare frame by frame what changed during those 21 hidden days behind the sun. On-Earth observatories will join in chorus. The European Southern Observatory in Chilliwack in Hawaii, Alma Gemini, Pan-STARRS, and hundreds of smaller telescopes scattered from Arizona to the Canary Islands will participate in a coordinated campaign, a symphony of optics stretched across hemispheres. Even amateur astronomers, those quiet custodians of wonder, will track the emerald blur from backyard domes and mountain ridges, knowing their modest data will merge into the global archive of human curiosity. In every time zone, the same thing will happen. Someone will step outside on a cold December night, point a telescope toward the right coordinates and wait for a ghost to appear. The world has done this before. Thousands of years ago, our ancestors gathered under open skies for the same reason to watch a visitor of light move among the stars. To them, comets were omens, heralds of death, birth, or change. The Chinese court astrologers recorded their shapes with brushes on silk. Babylonian priests carved their appearances into clay. The ancients could not measure or explain, but they felt the significance. Every unexpected light in the heavens reminded them that the cosmos could still surprise. Now in the age of spectrographs and orbital mechanics, the ritual endures. We've replaced superstition with simulation, prophecy with probability. Yet beneath the mathematics, the same pulse beats the awe of watching something older than our civilization glide across our sky, indifferent, yet mesmerizing. For astronomers, the December encounter is the culmination of months of modeling, anticipation, and restraint. The object's reappearance will answer the most immediate question: did it survive perihelion? If it emerges intact, its nucleus will gleam brighter than ever, a solid body defiant against the sun's furnace. If it fragmented, its pieces will scatter into a fan-shaped debris field glowing with fresh dust. Either way, telescopes will record and humanity will know. But even that answer, clear and factual, will open new mysteries. If its orbit remains unchanged, 3 Atlas will continue outward, returning to interstellar night, the third and largest of our known interstellar visitors, a messenger passing through. Yet if its path has shifted, if the sun's gravity has captured it, by even a fraction of velocity, then we may be witnessing the first interstellar object ever bound to our system. That possibility, faint, almost absurd, electrifies the waiting, because it would mean this alien body born around another sun will remain here circling our own, a permanent thread in the solar fabric. It would make the transient eternal. Across universities, labs and living rooms, the countdown ticks on. Data teams prepare pipelines. Observation schedules synchronize. On December 19th, thousands of machines, from the largest mirrors to handheld lenses, will all look to the same coordinates. And in that global gaze lies something rare and unifying. For once, all eyes will turn not toward one another, but upward toward a visitor from beyond, an uninvited but somehow welcome reminder of how small and curious we still are. In a sense, it's a return to the oldest human instinct to lift our heads toward the unknown and feel both fear and gratitude. The same emotion that once led priests to interpret comets as divine messages now drives engineers to fine-tune instruments at Lagrange points. The tools have changed, but the longing has not. Soon, the emerald flame will reappear faint at first, then sharpening through lenses and mirrors carried to screens across the world. Children will see it in live streams. Astronomers will plot its light curves. Poets will compare it to omens and forgotten gods, and somewhere under the quiet December sky, an observer will look up, feel the chill of the night, and realize that across the centuries from clay tablets to CCD sensors, humanity has always been doing the same thing, standing beneath the stars waiting for the sky to speak. The limits of our vision. Every telescope is in the end a listener. It does not touch, it does not smell, it does not hold. It simply waits for light, tiny messengers that have travelled unfathomable distances to whisper the story of where they've been. That is the quiet truth of astronomy. It is a science built not on things but on signals. Every photograph, every spectrum, every data point we cherish began as a single photon crossing the void for years, centuries, sometimes millennia, before finally brushing against a mirror or a sensor. What we call seeing the universe is really catching echoes of brightness that began long before we asked the question. When the James Webb and Hubble telescopes turn toward 3i Atlas, they do not see it the way the human eye might see a stone or a leaf. They sense the reflection of sunlight, the shimmer of gas molecules, the faint warmth radiating from dust. From these traces we reconstruct shapes, temperatures, compositions. We can map a surface, measure its rotation, and even infer the behavior of its coma. But beneath that surface, inside the nucleus, within the core, we are blind. No telescope can tell us whether 3i Atlas is solid or hollow, fractured or fused. The photons that reach us carry only information from the outermost layers, a thin shell of reflection and emission. Everything deeper than that remains hidden, sealed behind light's final frontier. Even radar, even spectroscopy can only guess at density and structure by the way light bounces or bends. We live then in a universe of surfaces. Astronomy is the art of inferring interiors from reflections, a discipline of luminous silhouettes. We imagine the heart of stars from their colour, the mass of black holes from the orbits of things they consume, the shape of a galaxy from a pattern of brightness fading into night. All we ever touch are photons, tiny tireless couriers of truth and illusion. In that way, science is an act of faith, not faith in mystery, but faith in light. We trust that the universe will tell us the truth about itself if we are patient enough to listen, if our mirrors are steady and our minds humble. We believe without proof that every flicker we see has meaning, that these particles of radiance can carry messages from places we will never go. Even now, light from 3i Atlas leaves its surface, crosses millions of kilometers of vacuum, and arrives at our detectors a few minutes later, the briefest delay on cosmic scales. Yet enough to remind us that we always live slightly in the past. By the time we see it, the event has already happened. The photons have already fled. There is something profoundly tender in that realization that the cosmos communicates only in memories. For the science for sleep listener, it is almost meditative. Imagine each particle of light as a traveler tiny and tireless, gliding through darkness for years, carrying a fragment of information no larger than a whisper. It journeys through cold space, past planets, and dust unimpeded, until one evening it lands softly on a mirror polished by human hands. There it releases its secret, a colour, a pattern, a pulse, and disappears. The scientist records its message. The photon vanishes. Only the story remains. That is the quiet transaction between cosmos and consciousness. Light gives itself away. We build meaning from its absence. And so when we speak of observing 3i Atlas, we must remember the humility of that verb. We do not see it as it is, we see only what its light allows us to know. A reflection, a shimmer, a ghost of energy telling us something true but never the whole truth. Perhaps that's why astronomy carries such a strange serenity. It asks us to accept partial knowing, to live peacefully inside the limits of perception, to find wonder not in mastery but in the patience of looking. For all our instruments, for all our billion-dollar mirrors orbiting in silence, the universe still keeps its interiors hidden. But that is not failure, it is invitation. Because every unanswered question, every unseen core, every photon that fades, before we can catch it, these are the spaces where imagination and science meet, where curiosity becomes a kind of love. So when the telescopes awaken this December, when their lenses open, and the faint light of 3 Atlas touches them, after weeks of darkness it will not just be observation, it will be communion. A reminder that even at the edge of knowledge, light continues to find its way to us soft as breath, patient as time. The question science avoids Every field of knowledge has its forbidden question, the one that everyone privately wonders about but few will say aloud. In astronomy today, that question is simple, almost childlike. What if it's not natural to even ask? It risks reputation. To answer it risks exile. And yet behind closed doors and private emails, many do ask softly, cautiously, like a confession. Because 3i Atlas, for all its data and definitions, still refuses to behave like anything else we've seen. Avi Loeb calls this the rating scale problem. Instead of labeling discoveries as natural or artificial, a binary that freezes discussion, he proposes assigning probabilities. A 0 means certainly natural, a 10 means unmistakably artificial. Most celestial objects sit comfortably near 0, but when an interstellar visitor breaks the rules of chemistry, trajectory and composition, all at once perhaps we are justified in giving it a 1, or a 2, maybe even higher. It is not a claim he insists, but a calibration of humility. Yet even suggesting such a scale invites scorn. In modern science, the worst sin is not ignorance, but imagination without proof. The frontier between curiosity and credibility is policed by ridicule. Peer review meant to protect rigor sometimes becomes a moat defending conformity. History remembers this pattern well. In 1610, Galileo Galilei raised a crude telescope to the night sky and saw 4 tiny moons orbiting Jupiter. To him it was evidence that Earth was not the centre of everything, that the heavens moved by rules beyond scripture. The establishment laughed, called his lenses tricks of glass. His discoveries were denounced not because they were wrong, but because they were inconvenient. 3 centuries later, Alfred Wegener proposed that continents drifted, that the map of the Earth was once a single puzzle, now slowly moving apart. His peers dismissed it as fantasy. He has no mechanism, they said. Rocks do not swim. Only after satellites confirmed plate tectonics did the ridicule fade, too late for the man who had died in the Arctic still defending his heresy. Science, for all its light, casts long shadows of habit. The pattern repeats because the structure of discovery demands it. New ideas threaten old investments, theories, reputations, careers. To acknowledge a radical possibility is to admit that our instruments might not just measure nature but reveal something beyond it. And that frightens even the boldest minds. So when Loeb writes about interstellar objects as potential artifacts, his peers respond with familiar phrases: extraordinary claims require extraordinary evidence. True enough. But history shows that extraordinary evidence often arrives only after someone dares to make the claim. The telescope comes before the consensus. Still, science is not a battlefield between believers and skeptics. It is a conversation between courage and caution, both necessary, both fragile. The skeptic demands proof. The dreamer demands possibility. Without the first, we drift into fantasy. Without the second, we fossilize. And perhaps that is why the question persists. Because even if 3i Atlas turns out to be nothing more than rock and ice, the fact that it invites the question of artifice is already significant. It means nature has reached the edge of what our imaginations can easily contain. There is a quiet bravery in wondering aloud. To ask if something might be designed is not to proclaim aliens. It is to acknowledge the universe's capacity for surprise. It is to practice what science often forgets: curiosity without shame. Galileo's telescope, Wegener's drifting continents, Loeb's rating scale, they are all expressions of the same defiant hope that truth is not diminished by laughter. Perhaps in time, 3i Atlas will settle into the catalogue of natural phenomena, its strangeness explained by chemistry or chance. Or perhaps decades from now, another object will arrive with the same impossible properties, and another generation will remember how the first question was silenced by politeness. For now, the debate endures quietly beneath the polished calm of conferences and the careful syntax of research papers. Scientists know what they risk by asking, but they also know that every great discovery began as a question someone was afraid to voice. And so in the small hours of observatory nights when the data hums and the stars drift across the dome, a few still whisper the unsanctioned thought: what if intelligence isn't unique to biology? What if the universe too learns to build? There is no shame in not knowing, only in refusing to wonder. The view from Mars. While Earth waited in blindness behind the sun, another world kept watch. Orbiting high above the red deserts of Mars, the Mars Reconnaissance Orbiter (MRO) carried on with its silent duty, mapping, measuring, and occasionally turning its instruments outward toward the wider sky. On November 6, 2025, just days after 3i Atlas slipped behind the sun from Earth's view, MRO's high-resolution imaging science Experiment high-rise camera was given a special task to catch the traveller mid-passage from an angle only Mars could offer. The geometry was perfect. From Mars's orbit, the object was not hidden, but visible, sliding just beyond the sun's corona in a patch of crimson dawn. Engineers reprogrammed MRO's attitude thrusters to tilt its gaze off the Martian limb, aligning its narrow field of view with precise celestial coordinates. It was a delicate maneuver. The spacecraft's sensors were never designed to track fast-moving interstellar bodies, but the calculation worked. Over 6 minutes of exposure, the high-rise camera gathered faint photons from a point source tens of millions of kilometers away. The data was compressed, transmitted back to Earth in packets, and reconstructed at the Jet Propulsion Laboratory 2 weeks later. The image was noisy, speckled with cosmic rays and compression artifacts, but unmistakable. Against the dark backdrop of stars, 3I Atlas appeared not as a single nucleus, but as something slightly asymmetric. Its coma, the envelope of gas and dust surrounding it, was offset, the brightest point displaced a few hundred kilometers from the geometric center of the glow. At first, mission scientists attributed it to a common phenomenon, jetting asymmetry. When gas vents erupt unevenly from a comet's surface, they can push the nucleus off-center, relative to its cloud of debris. But as analysts refined the image, some began to wonder if the pattern hinted at something else. Two faint cores seemed to shimmer within the coma twin knots of brightness less than a pixel apart. Was it a binary nucleus, a comet that had split under solar stress? Or could it be a trick of perspective, the echo of motion across multiple exposures, an optical illusion created by a camera designed for landscapes, not stars? Others whispered another possibility more radical, though never formally written down, that the 2 points of light were not fragments, but the inner and outer surfaces of a hollow shell, sunlight scattering through a thin membrane of material. A geometrical effect, perhaps, but one that aligned eerily with earlier density, estimates suggesting impossible hollowness. No one could say for sure. The signal-to-noise ratio was too low, the image too coarse. A follow-up attempt was scheduled but aborted. MRO's solar panels had to reorient to maintain power, ending its brief foray as an interstellar observer. And so what Mars glimpsed remains ambiguous, a half-seen shape suspended between interpretations. 2 cores, 1 hollow. Artifact or truth? For weeks afterward, analysts argued over brightness profiles and pixel histograms, each claiming a different certainty, each haunted by the limits of what one frame of light could reveal. But in that uncertainty lies the poetry of distance. Mars was the only world that could see what we could not. And yet even from there, even with a camera built by human genius and patience orbiting a planet we've already conquered with robots, the image was still incomplete. A smear of photons, a hint of form, a question disguised as data. The farther we look, the more ambiguity becomes our native language. Astronomy lives in that tension between clarity and blur, between signal and imagination. Every observation is a conversation interrupted by light years, every conclusion a guess dressed in numbers. We ask the universe what it is, and it answers in half-phrases and echoes. Perhaps that is fitting. Perhaps the cosmos withholds its certainties so that curiosity never runs out of work. And so the view from Mars joins the archive, a single image, faint and imperfect, showing a traveller that refuses to resolve into one thing or another. Was it 2? Was it hollow? Was it merely a trick of the camera's tired eye? No one can say. Only that in those few seconds of Martian time, a distant machine caught a glimpse of something that seemed to shimmer between realities, a riddle suspended in sunlight, framed by the thin atmosphere of a world that once watched its own skies for signs of life. Ambiguity, it seems, is the tax we pay for distance. The universe lets us see, but never quite enough to be sure. The radio silence. As 3 Atlas approached, its perihelion telescopes across the world turned to catch its light. But another kind of listening began as well, one that dealt not in brightness, but in quiet. In October 2025, the Breakthrough Listen initiative quietly added the object to its observation roster. Funded by the Breakthrough Foundation, and operating from the Green Bank Telescope in West Virginia and the Meerkat Array in South Africa, it is humanity's most sensitive search for extraterrestrial intelligence, a vast ear pressed to the cosmic sea. Its task was simple in principle, and profound in implication: to listen for any radio signal that might originate from 3I Atlas, any narrow-band transmission too orderly, too precise to be natural. For 2 weeks before solar conjunction, The project devoted several observation sessions to the object. They scanned across the L-band 1-2 GHz, the S-band 2-4 GHz, and higher frequencies where human technology tends to whisper. Their receivers can detect a signal as faint as a cell phone broadcast from the distance of Jupiter. In theory, even a low-power transmitter aboard a small probe could have been noticed. No such signal was reported, at least none released publicly. SETI researchers are careful with language. They do not say nothing was heard. They say no candidate signals of interest were detected. The difference is subtle, but important, an admission not of certainty but of limits. For all its power, breakthrough. Listen covers only a thin slice of possibility. The radio spectrum is vast and cosmic noise is everywhere. Even the most sensitive equipment can only listen to one narrow channel at a time and for a few hours at best. The universe, meanwhile, broadcasts across trillions. If 3i Atlas or anything aboard it were sending signals outside those windows, we would never know. If it spoke in frequencies below 10 milliwads, the Earth's ionosphere would block them. If it used tight beam communication aimed elsewhere, we'd never intercept the whisper. That is the sobering humility of our technology. We have built great ears, but not infinite ones. And so the data logs came back, filled with static, filtered, cleaned, and stored. A report was drafted, reviewed, and filed under no detection. The rest of the world caught up in the object's optical mysteries, its mass, its trajectory, its emerald glow, barely noticed. The other silence not of light, but of radio. But silence itself can be eloquent. Astronomers like to remind each other that absence of evidence is not evidence of absence. The phrase older than CT itself has become its quiet mantra. We listen not because we expect an answer, but because we believe the cosmos is large enough to surprise us. When the microphones come back empty, it is not a failure. It is simply another reminder that most of space hums below our threshold. Consider the analogy often told among SETI scientists. Imagine standing on a beach holding a cup, dipping it into the ocean, and finding no fish inside. Would you conclude the ocean is empty, or simply that your sample was small and the sea immense? The universe is that ocean. We listen with our cups. Perhaps there were signals, but faint, scattered or encoded beyond our understanding. Perhaps there were none at all. Or perhaps 3i Atlas, if it is artifact rather than accident, is simply asleep, a derelict machine drifting in interstellar night, dreaming in silence. In a way, the metaphor extends beyond astronomy. Whales sing in the deep ocean at frequencies that travel hundreds of miles, their songs slipping beneath our human range of hearing. For centuries we believed the seas were mute until we built microphones to listen properly. The songs were there all along, we were just deaf to them. Maybe the same is true of the cosmos. Perhaps signals fill the vacuum hums of civilizations long gone, still echoing through the electromagnetic dark, but we haven't yet tuned our instruments or our imaginations to hear them. Silence, then, is not the universe's rejection of us. It is its most patient form of invitation, because every time we point a dish toward the stars and hear nothing, we are reminded of the magnitude of what remains unspoken. The radio quiet of 3 Atlas is not proof of emptiness. It is proof of our willingness to listen. Somewhere out there, perhaps another listener does the same scanning, waiting, wondering if they too are alone. Between them and us lies only distance and the shared ocean of quiet that makes meaning possible. The December window opens, at last the long night of waiting ends. By early December, sunlight shifts, angles realign, and 3i Atlas begins to slip free of the sun's glare. The December window, the brief period when Earth can again observe the visitor without blinding interference, has opened. 10 nights, maybe 12 if weather and fortune agree. 10 nights that may either rewrite textbooks or quietly affirm them. Across the world, the machinery of curiosity awakens. From Hawaii to Chile, from the Canary Islands to the deserts of Australia, telescopes begin to turn in synchrony. On orbit, the great eyes of Hubble and Webb wait for precise alignments, their instruments cooled, calibrated, and tuned like orchestral strings about to play in the dark. This time the campaign will cover every wavelength the human mind can reach. In optical light, the broad white glow of reflected sunlight will be tracked by dozens of observatories. Each photon will tell of surface brightness, coma, evolution, and rotation period, how the visitor spins, whether it wobbles, whether it hides fractures under its luminous veil. In the infrared, the James Webb Space Telescope will read temperature like Braille across its dust and gas. Infrared light pierces through glare and shadow, revealing what no visible spectrum can: the hidden warmth of sublimating ice, the glow of dust grains heated by sunlight. It is there that scientists hope to find fingerprints of molecules, complex organics, carbonyls, cyanides, tiny signatures that might finally explain the green fire, the chemical imbalance, the whisper of nickel without iron. Ultraviolet instruments aboard Hubble and Swift will join the chorus. They will seek the electric blue of ionized gas, tracing how solar radiation strips electrons from atoms, how sunlight itself sculpts the object's outer skin. In those bands, a comet's heartbeat becomes visible, the pulse of energy that reveals its vitality or its exhaustion. Meanwhile, from ground-based telescopes in Chile and Spain, a quieter technique will be used: polarimetry, the study of how light waves twist when reflected from different surfaces. Polarized light carries hidden geometry. A rocky surface, an icy crust, or a metallic shell, each rotates light in its own peculiar way. To measure those shifts is to glimpse texture, not through image but through mathematics. The data streams are immense. Every night, terabytes of raw starlight are compressed, encrypted, and ferried across oceans of cable. Algorithms hum, servers glow. The world's observatories, scattered across continents and orbit, now act like a single organism, inhaling together the planet's collective gaze, synchronized by mathematics and hope. In control rooms and mountaintop domes, humans play their ancient part, waiting. Someone checks exposure times. Someone whispers coordinates. Someone pours coffee and watches clouds roll over a dome that must remain open, praying the wind doesn't rise. Through this network, this web of eyes and minds, Earth breathes in rhythm with the cosmos. The campaign runs from December 10th to 20th, 10 nights stitched together across latitudes and longitudes, each hemisphere handing the baton of night to the next. When one sky brightens, another darkens. When one telescope sleeps, another wakes. For the first time in history, humanity's instruments form a kind of planetary heartbeat. We are no longer a species of isolated watchers. We are a global sensor, each aperture and eyelid opening toward the same enigma. And yet beneath all the precision there remains the thrum of emotion. Every astronomer, from graduate student to principal investigator, knows the stakes. These 10 nights could render half a decade of debate irrelevant or immortalize it. If 3i Atlas behaves as a comet should, the mystery will dissolve into familiarity numbers returning to comfort. But if the data diverge, if the polarization curves twist unexpectedly, if infrared spectra reveal hollow echoes, if its path deviates even slightly from prediction, then something vast will shift. The textbooks will not close, but they will begin to whisper new sentences into their margins. Outside the domes, December air grows still. In the Atacama, the wind pauses. In Mauna Kea's thin atmosphere, frost glitters on rails. The telescopes pivot in unison, their motors humming softly, as though the planet itself were inhaling a single breath, shared by thousands of mirrors, thousands of minds, all waiting for one object to rise. When it does, small, green, distant, its light arrives as a faint shimmer against the noise. Not bright, not loud, but enough. Photons that left it minutes ago now spill across detectors, translated into data, into graphs, into wonder. And in that moment, those first clean exposures after months of absence, the world feels united by curiosity alone. 1,000 humans scattered across Earth, staring into the same patch of darkness, asking the same unspoken question. What are you 10 nights to find out? 10 nights of breath and data, silence and light. The December window has opened and the universe for once seems willing to answer. Questions without answers. By the close of December, the data begins to pour in terabytes of light, thousands of spectra, tens of thousands of photographs. Yet for all the technology, all the precision and patience, the story of 3i Atlas still ends as it began, with questions that refuse to resolve. We know its orbit, but not its origin. We know its brightness, but not its structure. We know its chemistry, but not its meaning. Is it hollow or solid, metal or ice? A shard of some lost world, or the shell of something built with purpose? Every hypothesis has evidence, none has proof. Even its color, that impossible emerald shimmer, continues to defy explanation. Too stable, too pure for the molecules we've measured. Inside its nucleus, if nucleus it truly has, might lie nothing more than frozen gas and fractured rock. Or perhaps something stranger, a geometry we cannot yet name, a structure that outlasted the star it once orbited. We will never know. Our instruments touch only the skin of things. Their hearts remain unlit. So we return to the beginning, to what we can know. The data confirms that 3i Atlas survived its solar passage. It did not fragment nor slow nor vanish. It emerged intact, scarred, glowing faintly, moving outward again into the deep. But whether its path was changed by a hidden maneuver, or whether it merely endured by chance, the record remains ambiguous. We are explorers listening through fog. We send our questions out like sonar pings into the dark, and what comes back is not the thing itself, but its echo, distorted, delayed, translated by distance. From those echoes we build maps of meaning, shapes of conjecture, the fragile architecture of knowledge. That is what astronomy truly is, the study of echoes. Our telescopes do not touch the object, only its light. Our equations do not capture the truth, only its reflection. We are like sailors of old hearing waves crash against invisible cliffs, guessing the shape of the coast by sound alone. And still we keep calling out. We call across centuries and across space, sending photon signals, metaphors. We call because the silence, though vast, always answers in some way, if not with clarity, then with wonder. In the end, through Atlas leaves us not with solutions, but with humility. It reminds us that science, for all its instruments and equations, is still an act of imagination. We draw conclusions from fragments we build, understanding from flickers. And sometimes what endures longest is not the data, but the feeling of standing at the edge of the known, hearing something faint and mysterious echo back. Maybe one day another interstellar visitor will come and its secrets will be clearer, its voice louder. Or maybe every visitor will always speak in riddles, as if the cosmos knows that mystery itself is what keeps us listening. For now we file our papers, archive the spectra, and close the observatory domes. The object fades outward, dimmer, slower, one more line on the star maps. But its trail glows faintly in the collective mind of our species, a thin green thread woven into the larger fabric of wonder. We still do not know what it is. We only know that it was here and that it changed the way we look at the sky. Perhaps that is enough. In the end, some questions are not meant to be answered, only asked beautifully. The parable of the forgotten comet. Imagine an astronomer in the year 1950. His observatory sits on a lonely mountain in New Mexico, or perhaps the Canary Islands, a domed sanctuary of glass, brass, and patience. Inside, the smell of oil and metal mixes with the cold of altitude. His telescope, heavy as a cannon, is made not of carbon fibre, but of polished brass and steel gears, its counterweights hanging like church bells. Each night he climbs the creaking stair to the eyepiece, checks the star charts pinned to the wall, and waits for the world to turn into alignment. His logbook, bound in cracked leather, is open on a wooden desk beside him. The pages are filled with numbers, coordinates, and quick sketches of smudges he's seen through the lens. His fingers are ink-stained, his handwriting careful but fading. Now imagine that on one of those nights he sees something new, a faint point of greenish light sliding slowly against the background stars. It has no catalogue number. It moves, but not like an asteroid. It gleams, but not like a comet. He notes it dutifully: unidentified object RA, with 1622 men, deck, Soposwozang, pale green hue. Possibly photographic defect. He records it, files the film plate, and moves on. Because in 1950 there are no theories of interstellar visitors. The idea that an object could wander in from another star system, that a comet could be, not ours, belongs to science fiction. The paradigms of his time do not contain that possibility, so he never thinks to follow up. A week later the green light fades from the sky and history forgets it. The plate remains in an archive, its mystery unnoticed for 70 years, a silent testimony to the limits of imagination. This is the parable of the forgotten comet. It is not about one man's mistake, but about the quiet blindness that settles over every generation when knowledge becomes comfortable. We build frameworks, models, equations, categories, and they serve us well until something slips between them. Then, instead of seeing it for what it is, we see only error. Our astronomer was not careless. He was obedient to reason, and reason in that moment betrayed him. His training told him to trust instruments, not intuition, to fit observations into known patterns, not invent new ones. The unknown became noise, and the noise was ignored. That is how paradigms protect us from chaos, and how they sometimes imprison us within it. The history of science is full of such ghosts, signals, misread discoveries, dismissed revelations buried in plain sight. The first pulsars were filed as interference. Continental drift was laughed out of conferences. Meteorites were once thought impossible because stones cannot fall from the sky. It is easy to smile at the past, harder to see ourselves in it. But one day, our own data, the terabytes gathered from 3 Atlas, the thousands of spectra, the models we worship, may look just as quaint. Future minds will browse our archives and find the places where we blinked, where something extraordinary passed before our instruments and we failed to recognize it. The parable is a warning, but a gentle one. It reminds us that the universe does not care for our categories. It speaks in every language at once, chemistry, gravity, light, and waits for us to imagine new ways of hearing. Recognition, after all, is not a matter of eyesight, but of imagination. Our forgotten astronomer did not lack vision. He lacked a story large enough to fit what he saw. Perhaps that is true of us too. Perhaps the next revelation is already captured on a sensor somewhere hidden among the noise, waiting for a mind unafraid to name it. The forgotten comet, like 3 Atlas itself, whispers the same message through time, what we cannot imagine we cannot see. What December may reveal. The window is open, the telescopes are awake. Around the world, servers hum, mirrors gleam, and data begins its slow journey from vacuum to understanding. But even now, as the first images of 3I Atlas return to Earth, no one knows what December will bring. There are 2 kinds of revelation awaiting us, and neither will arrive cleanly. The first is the quiet satisfaction of confirmation. If every wavelength optical, infrared, ultraviolet radio behaves as expected, then 3I Atlas will settle comfortably into the catalogue of natural phenomena. Its mass will find reconciliation in refined models, its green glow in updated chemistry, its improbable orbit in the long statistics of cosmic chance. The story will shrink from mystery to case study, an unusual comet, yes, but one that still obeys the universe's rules. The second possibility is the return of strangeness. Perhaps the polarization data will misalign, or the coma's symmetry will break in ways no simulation predicts. Perhaps the mass will still refuse to match the light it reflects, or the trajectory will deviate subtly from prediction, a few arc seconds of doubt that unravel everything. And perhaps within that sliver of uncertainty, science will have to pause again and whisper we don't know. It's not failure, it's the rhythm of inquiry. Science advances through ambiguity not in spite of it, but because of it. Each unanswered question becomes the seed of the next experiment, the quiet reason. Another telescope must be built. Peer review, often caricatured as bureaucracy, is in truth a collective meditation on uncertainty. Dozens of eyes re-examine each dataset, each statistical fit, trying not to prove but to remove illusion. Consensus does not arrive like revelation. It accumulates like frost particle by particle until the pattern holds. And yet beneath that discipline there are always the human beings tired, blinking coffee-stained, staring at screens in the half-light of dawn as the first raw telemetry arrives. In control rooms in chilly Hawaii, Pasadena, Cape Town and Canberra, the same ritual repeats, data bars crawling upward, the slow exhale of relief when a connection holds the whisper of numbers turning into images. Somewhere a graduate student clicks download at 3:00 a.m. and watches the universe appear, pixel by pixel, a soft green smear, perhaps nothing new, perhaps everything. Somewhere else, a principal investigator rubs their eyes and mutters to a colleague, maybe this time we'll see inside the mystery. They know the odds. Most mysteries dissolve in data. The cosmos, when magnified enough, usually becomes ordinary again. But still every dawn feels like a gamble worth taking. For 10 nights, humanity will live in that liminal space between ignorance and illumination. The telescopes will feed the world with light and noise. Analysts will sift, compare, argue. Hypotheses will rise and fall in academic journals like waves. And when it's over, when December yields its verdict, the outcome will be less a conclusion than a reflection of who we are, a species that measures doubts, dreams, and tries again. If the data confirm naturality, we will celebrate the elegance of physics, the power of probability, the quiet triumph of patience. If new anomalies appear, we will celebrate something else, the persistence of mystery itself, the proof that the universe still outpaces our imagination. Either way, wonder wins. So as dawn breaks over observatories and the first hard drives fill with starlight, the researchers watching those green smudges on their screens are not just scientists. They are the latest in a lineage of watchers, monks of data keepers, of the candle of curiosity who stay awake so the rest of us can dream. And outside beyond the frost on the domes, 3I Atlas continues its quiet arc through sunlight indifferent to our scrutiny, yet somehow the reason we are looking at all, the cost of being wrong. By the time the December data are fully analysed, every possible interpretation will already have defenders and dissenters. That is how discovery always feels, at the edge, a conversation stretched between caution and courage. But beneath the graphs and equations there lies a quieter tension, one that science rarely names aloud: the cost of being wrong. If 3I Era Atlas is entirely natural and exotic but ordinary product of physics, then every hour spent imagining intention will look naive in retrospect. The skeptics will be vindicated, their restraint recorded as wisdom. To them the danger was not missing wonder, but mistaking wonder for evidence. The universe, after all, has fooled us before, but if it is not natural, if somewhere in its motion or chemistry or silence lies a trace of design, then disbelief will be the greater blindness. To dismiss the possibility of intelligence beyond our own would mean turning away from one of the most profound encounters in human history. The risks are not symmetrical. To believe too soon invites ridicule. To doubt too long risks missing revelation. This is the paradox every frontier faces explorers standing on strange shores, trying to decide whether the land before them is a continent or an island. Columbus mistook the Caribbean for Asia, but he was also right that another world existed beyond the maps. The early astronomers saw canals on Mars, and though they were illusions, the dream of connection they inspired eventually gave rise to real exploration. Error too can be creative. Science lives in that tension. Skeptics guard its integrity. Dreamers guard its possibility. They are not enemies, only opposite poles of the same compass. One asks, how can we be sure? The other whispers, what if we're not wrong? Between them lies the fragile balance that keeps humanity moving forward without falling into fantasy. And perhaps both deserve empathy. The skeptic carries the weight of responsibility, the fear of leading others astray, of mistaking noise for signal. Their armor is data, their weapon patience. Yet even they know that absolute certainty is a mirage. The dreamer carries the burden of ridicule, the fear of believing alone, of reaching too far. Their fuel is hope, their weakness faith. Yet without them no telescope would ever have been built, no probe ever launched into the dark. To be wrong in either direction is to be human, but to refuse to risk wrongness, that is to stop learning altogether. Perhaps the real question is not which side is correct, but which mistake we are willing to live with. The error of false wonder or the error of lost wonder. Because the unknown is not an adversary to be defeated, but a mirror. It reflects our choices, how we weigh caution against curiosity, pride against humility. 3I Atlas, indifferent and silent, merely provides the test. In the coming months, papers will be published, conferences convened, debates replayed. Some will declare closure, others will insist the mystery deepens. But long after consensus forms and fades, what will remain is the feeling, that fragile awe of realizing we might have glimpsed something beyond comprehension, and that the line between artifact and accident is as thin as a photon's path. If we are wrong about 3I Atlas, either way, we will learn. If it is natural, we will expand our definitions of nature. If it is not, we will expand our definition of ourselves. And so we continue, skeptics and dreamers sharing the same sky, making different bets on the same question. Not because we expect to win, but because the act of asking keeps us alive. For in the end, science is not a fortress of certainty, but a voyage through humility. And every voyager knows the only unforgivable error is refusing to set sail. The threshold of December. By mid-December, the excitement has quieted into something more solemn. Not disappointment, not fatigue, but the stillness that follows long vigilance. The observatories keep their watch, but the sky has grown calm again. The great alignment has passed. The green glow of 3I Atlas drifts outward, dimming night by night, its mystery no longer urgent but eternal. Institutions continue their work. Committees review data, peer reviewers annotate margins, agencies prepare cautious statements. Science, steady and disciplined, moves at the pace of consensus. It does not leap, it walks. And in that deliberation lies both its strength and its sorrow. For even as new instruments awaken to record the heavens, others grow hesitant, not for lack of vision, but for fear of being wrong. In that hesitation, a question hums beneath the surface. Would we even recognize the extraordinary if it stood before us? Perhaps we are not limited by technology, but by imagination, by the cultural gravity that keeps us orbiting what feels safe to believe. The astronomers who stayed awake through the long nights know this feeling intimately. They have seen the raw data, the noise and beauty mixed together like static and song. Some sense a pattern, others see coincidence, yet all share the same quiet awe that they have looked directly into the unknown and found it neither hostile nor kind, simply vast. Outside the laboratories and control rooms, the rest of the world continues its December routines, shopping celebrations, the closing of another year. Few notice that high above the clouds, the telescopes are still gathering the last glimmers from a visitor that has already begun to leave us. The public imagination has moved on, as it always does. Mystery fades when the next light appears on a screen, but not for the watchers. On the night of December 15th, the final scheduled exposure completes. The domes rotate shut, the red lights of control panels dim. In the cold before dawn, the last photons from 3i Atlas travel through the atmosphere and touch the mirrors one final time. Then they too are gone. It is a small ending, quiet, procedural, yet somehow transcendent. For in that stillness we glimpse the soul of science, not in answers but in the act of looking. Humanity has built machines to pierce the darkness, and what they reveal is not certainty but wonder. We are, after all, a species learning to listen to the universe without expecting a reply. There's a melancholy wisdom in that what some thinkers call the dark forest paradox, the idea that space might be full of watchers, each too cautious to speak. But perhaps the silence is not menace. Perhaps it is grace, the universe granting us the time to learn how to ask gently. For now we have only echoes, equations, and light. But that is enough. Every photon we collect is an act of reverence, every spectrum a small prayer to understanding. We do not need 3 Atlas to be alien or miraculous for it to matter. Its passing, like all celestial visitors, reminds us that curiosity itself is the miracle, the fragile courage to notice, to wonder, to ask questions that may never be answered. In the quiet after the final observation, one can almost hear the universe breathing not as emptiness, but as presence. The same calm that lived in the hearts of ancient skywatchers lives in ours now, the humility of standing beneath an infinite sky, and realizing that not knowing is its own kind of peace. So we close the domes, archive the data, and turn homeward. Above us, 3i Atlas fades into the night beyond Jupiter, leaving behind only the faintest trail of green, the afterimage of a question we were brave enough to ask. And in that fading there is gratitude. For mystery does not diminish us, it completes us. It reminds us that we belong to a universe still capable of surprise, that to be human is to reach for meaning even when none is promised. The telescopes sleep, the sky turns, the year draws to a close, and in the soft rhythmic hush between certainty and silence, a final thought drifts through the mind like a lullaby. Perhaps mystery is how the universe keeps us awake to wonder.